So, yes.
But actually, then what
Okay, so someone has about section 4 and homework 2. Part B says maximize the minimum reduction achieved over all highway rates. Now let's say that you have $100 to distribute to 5 people. Okay? You can allocate it any way you like. So, of course, to every such allocation, I could assign a measure of quality. So, you may assign $20 to each person. You may assign 5 to one, 95 to another, and nothing to the remaining 3, and so on. Of course, one measure of quality, and you may also just not assign anything to anyone and keep everything to yourself. So one measure of quality might be the total amount that you actually allocate, that you give away to people. Another measure of quality might be to look at the person who's worse off, who gets the least amount, and make sure that, you know, if I use that as a measure of quality, and I ask you to maximize that measure, then you would want to allocate as evenly as possible, right? So to any allocation, I could assign a certain measure of quality. Part A just says it's the sum of the reductions that you achieve, and part B, you know, if you look at the vector of reductions, look at the smallest possible reduction that you observe. That is the measure of quality, and I want that to be as large as possible.
do you mean that you have to allocate all D, like?
You don't have to allocate all D, but of course, if you have somebody unallocated, you could assign it to the first, you know, to the segment that achieves the smallest reduction and improve it. Okay? So in an optimal solution, you would end up allocating all D, but you don't have to. Just yes. I believe so. But I don't see any light. That's okay. So what do I do? There is an extra battery. I don't know if that's good. Is that better, you think? No, this is Duracell. Yeah, Michael Moscow. I don't know if he's here. So okay, good. Okay, good. I think we'll resolve this by end of December. Okay, so sorry about that. Does that answer your question? Yeah. Okay, so you look at, I mean, for part A, you look at all the reductions and you add. That's what you want to maximize. For part B, you look at all the reductions, you pick the minimum one. that quantity is what you want to maximize. So in particular, it's better to distribute all the reductions more evenly, even if it means the total reduction is much less, than it is to, to assign all the people to that segment that achieves the maximum reduction. So, any other questions about the homework? So in general, we've had two homeworks, both of them are sort of preliminary, but what is the general sense of the difficulty of a problem? About right? That means it's too easy. Thank you. No, seriously, I mean, would you, so obviously I don't want to bore you with trivial things here. Okay. So the pace of the class, of course, will also pick up fairly soon. We've been going through some fairly basic stuff about linear programming, and we'll study more theory over the next 2 or 3 lectures, and not just one. Next 2 or 3 lectures. Okay, so today what I'd like to do is to first go through a little Excel example. So I'm just going to solve the same problem that we solved in class over the last lecture. Show you how you can input it into Excel and actually get a solution, and also tell you about all the other stuff that Excel will give you, about which we learn over the next 2 or 3 lectures. That's what I want to do for the first 20 minutes or so, after which we'll get into the difficulties of the simplex method that we briefly discussed last time. In particular, how you initialize the method and how you prove that this will always converge to an optimal solution. So, now if you want to use Excel to solve a linear program, there are a couple of steps that you want to do for that. So first of all, let me write down the LP that we'd like to solve. It's maximize 2x1, 3x2, minus x1 plus x2 y, x1 plus 3x2 is at most 35, x1 is at most 20, and x1, x2 is not negative. And we already know that the optimal solution V star is 55. That's the optimal value. And I guess the optimal solution was 20 and 5. Right? So this is what we observed. Okay? So how do you solve this in Excel? Well, first of all, I assume everybody has used this piece of software, so let me make this bigger. I don't even know how I can get rid of this.
Right click and hide.
Okay, so you want to go to Tools to make sure that Solver is installed. If it is not installed, so if it is there, then you would actually see it in the Tools menu. Okay? So if it is not there, you would want to go to Add-ins and add it in. And Solver comes as a standard add-in to Excel. So pretty much any recent version of Excel should have this installed. Okay? So right now we already have solvers, so we don't have to worry about this. Then you want to input this linear programming problem. Of course, this is a small linear program, so you can actually type in everything. If you have a bigger linear program, then you may want to build some kind of an interface to actually read this LP in a certain format from a file. So I'm not going to get into that, mainly because I don't know how to do it. So, I mean, my knowledge of Excel is very limited. So, but this is what students like to use, so I've learned a little bit to get by. Okay, so how do we input this? Well, I think it's good practice to set up names for columns and rows. So let me just call this the X1 column, the X2 column, and this is going to be my constraint 1, constraint 2, constraint 3. Here's my objective function, and these are the values for the variables. Okay, so in a little bit you will know what exactly these things mean. So for now, let's actually look at constraint 1. Okay? Constraint 1 says minus x1 plus x2. So I put a minus 1 there, I have 1 here, and I want to say this is less than equal to 5. Okay. So this is my RSS. This is constraint 2 says x1 plus 3x2 is less than equal to 35. And constraint 3 says x1 plus 0x2 is less than equal to 20. And my objective value coefficients for x1 and x2 are 2 and 3 respectively. Okay. So far all I've done is just input the numbers into the appropriate column.
What about the last one, x1 and x2, bigger than 2?
X1, okay, just a second. So far all I've done is input numbers into the appropriate column so that somebody who's completely unfamiliar with Excel or with anything else, but just knows what a linear program is, can sort of reasonably infer what this problem is. So far we have not discussed, we have not done anything with Excel. We're just using it as some basic placeholder for all of this data. Okay? That's all we've done. I have omitted non-negativity constraints. Okay? I have also omitted the maximization objective. So these are two things that we have not yet done. So let's just mark those. Okay, so now we actually want to tell this piece of software that what we want to do is find values for x1 and x2 such that this objective function is maximized and the allowed values for x1 and x2 are non-negative. So we want to tell Excel this. Now, suppose I take x1 equals 1 and x2 equals 1. So this row number 9 in this spreadsheet, which is labeled value, is supposed to actually hold, so these two cells are supposed to hold the optimal values for x1 and x2. Okay? So first we want to understand what, suppose I set x1 to 1 and x2 to 1. What really should happen? Okay? So first of all, I want my objective to be 2x1 plus 3x2, which is 2 plus 3, 5. Okay? So in order to do that, we can say that so I go to this cell, let's go to this cell, and say that the objective value for any x1, x2 is going to be a sum product of row 9 with row 7. Okay? So what do I mean by that? Let me actually do this first, and then So I've done something very simple, which is worth looking at. So all I've done here is the following. If you look at this stuff here, it says sum product B7 colon C7 comma B9 colon C9. So all that does is the following. Anything, the entry in this cell, okay, is going to be a scalar product of row 7, the BC components, with row 9, the BC components. So it's going to take row 7, which has 2, 3, and it's going to take row 9, which has 1, 1, and it's going to compute the product 2 times 1 plus 3 times 1. Okay. So this is called a sum product because it computes the product and then it does a sum. And in general, no matter what values I have here, when I have x1 and x2, what's computed is 2x1 plus 3x2. So that's what a sum product function does. So for instance, now I can change this to 3 and 3, and I get 15, which is the right number. I could change this to 20 and 5, and I get 55, and so on. Okay. So a spreadsheet is just this, right? You can have cells containing data and cells containing operations on data. Now, if you change the data in certain other cells, all the operations are redone with respect to the new values of the cells, and you get an updated spreadsheet. This is what spreadsheet computation is. Okay. Any questions about this so far?
Could you just show us the command related like sum product?
Yes. So the command is, so one way to see the command would be to just go to that cell, and you see sum product has B7 colon C7, which is exactly this row. Okay. If you have many variables, you will have many more columns in your in each row, and you will have B7 colon G7, right, or whatever it is. And you put a comma, and you have the corresponding coefficients involving the objective. Involving the value.
We have like more cells after the C7, which is attached to the client, like by separate by column.
Exactly. So if you have more variables, you just use more columns for your variables, and your sum product will involve all of those variables. Any other questions? Okay. So at least now we know values. If I assign any value, 33 and 79, I get the right objective values. Okay. Of course, certain values for these, cells are valid, and certain values are not. What I've written down now, 33 and 79, violate the constraints. Okay. So you want to capture this as well. So how do you do that? Well, what does it mean for you to satisfy the first constraint? So the way you satisfy the first constraint is by looking at the sum product of this row, row 4, those two columns, with row 9, and checking whether that quantity, that sum product, is at most 5. Okay. That's what it means to satisfy the first constraint. So what I should put here is the following. So I should say some product B4 colon C4 comma so this cell now reflects the scalar product of the coefficients of the first constraint with the particular values that you've chosen for x1 and x2. Okay? Is everyone comfortable with that? So so now I want to do the same for the remaining two constraints. So what I could just do a copy and paste. So I could just go here, copy, paste. So notice that when I just copy this and paste it here, the 4s all automatically become 5s, right? So this is the only formula that I actually typed out. When I put it here, the 4 became a 5. And when I put it here, the 5 became a 6. So if you want Excel to do this, then you just use regular numbers. Notice also that when I did that copying, the 9 remained the same. Okay? So it's not as though everything went up by 1. It's exactly what we wanted. Okay? So whenever you want Excel to not increment as you do this pasting, you want to put a $ before the number. Okay? So this is absolute cell reference as opposed to relative cell reference. And this is an Excel thing that's useful, so they say. Okay, so now we have written all the constraints of the problem. At least we haven't actually told Excel that there is a constraint, right? Just as we haven't told Excel that there is an objective. But the way we set things up, we know that for us to satisfy this constraint, this inequality has to be true, right? Excel does not yet know that such an inequality exists, but visually we see that the values that I've put down here are unacceptable because 46 is not less than 5, 270 is not less than 35, and so on. Okay? So now we already know that we want to find values for these two cells, okay, such that whatever we get here, this entire column, is less than equal to this entire column. And among all values satisfying that, we want to maximize the value of this cell. Okay? So this is the basic setup that you need before you invoke solver. And it's in general a good idea to make sure, to just try various values and check that you have not made any numerical errors before it continues. Okay? So I could, of course, go back to 1 and 1 and everything changes. And this is feasible. So now you have a better way of solving a linear program than just adding a step. You could just do 2 and 3 and maybe keep doing this, keep on trying various numbers, hoping that you get somewhere. Okay, so now what do you do? How do you actually solve? So what Excel would do, for instance, is actually try various values for x1 and x2, such that all of these restrictions are satisfied and such that this value is maximized. It would actually implement some version of the simplex method that's what's behind all of this. So how do you invoke solver? Well, go to tools, call solver, and now we want to set various things, right? So this is where we tell Excel that we want to maximize this quantity
We want to satisfy all of these constraints, and we want non-negativity and so on. Okay? So the target cell is actually this, right? So this is our target cell, and we want to maximize it. Okay? Then there is something called by changing cells. So those are your variables. Those are the cells whose values are allowed to change. Excel has the freedom to set the values for those cells, and those are given by these two. Okay? So when you just select it, it automatically gets updated. So you don't have to type in anything. Then subject to the constraints, so you can add all the constraints. So when I click on add, I get a little add constraint button. And I could say, this quantity has to be at most this quantity. Okay? So that's added. Then we want this quantity to be at most this quantity. So I clicked OK, which means Excel thinks that those are all the constraints, but we want to add one more, so we could add this, this, this. So this, if you think about it, this is exactly the linear program that we have. It's encoded in a slightly different way. That we want to maximize a certain cell, subject to the values of certain cells being less than or equal to the values of certain other cells. Okay. Then we want non-negativity. If you go to options, you can say assume non-negative, for instance. You could say also assume linear model. You don't have to, but you could say that. So let's actually, saying assume linear model makes it easier because, so far, Excel has no idea whether what you've done is a linear program or not, right? Because it only looks at values of cells. And so if you tell it that you're actually solving a linear program, it invokes a different piece of software which is more efficient. So let's actually assume linear model. And now, you just say solve. And you solve it, right? Yes.
Do you have to, the solver can there's a guess for the objects. Do you want to just run that real quick?
Okay. So let me get to that in a little bit. Okay. So for now, I just want you to observe that it actually found the solution, which is always good, especially when you know it's right. It actually has a few other things as well. Okay, so let me again go back to solver. Okay, so you want to know what this is. Okay, so you got me there. I have no idea what that is. Yes?
What that does is just trying to look at all the equations you have in your spreadsheet and guess what the variables are.
Oh.
So if you have you don't know what the variables are, you can have Excel try to figure it out. That's, most of the time it's wrong.
Why am I not surprised? Okay, anyway. So let's actually go to options. Okay, and
Okay. So when you solve it, you also have the option of getting these additional reports, okay, which tell you which give you more details about the solution itself. It gives you various other information that are potentially useful, and we are going to study how one gets all of these a bit later, over the next lectures. But let me actually show you the forms of those reports. So first of all is the answer report, right? So this says, your objective value in the optimal solution is 55. It says original value. That's because I solved it twice. So, you could. Let me actually get rid of that. So maybe easier. So let me invoke solver here. Okay. So you started out with 0. You could actually give Excel some reasonable guess for a solution. Okay, so you could just say 1, 1, or whatever you think the solution is. And that may speed up things if you're solving a nonlinear programming problem where the initial starting point may be more important. But anyway, right now, it just says that the objective value is 55. It says this is the optimal solution, and these are the constraints. There is a slack of 20 in the first constraint, and the second and third constraints are binding, which means they are satisfied as an equality. Okay? Yes?
I have just a question about this. When you save this sheet, the book, are you going to be able to save the solver as well? Like, next time you open it and click the solver, it's actually there?
I don't know. I would assume so,
yes.
but I don't know.
So will you download the edit, then it's going to be. Okay, so if it's going to be there, would you mind sending us an email with an attachment? Oh no, you have to download the program.
Okay, so the question really is, would I be able to actually send you an email of this XLS file with the LP encoded? Yes. So I can certainly do that. It's not a problem. There's also, anyway, let me finish discussing the various reports, and I'll tell you other sources where you can get more information about these things. Okay, so this just gives you basic information about the solution itself. It tells you what the objective value is, what the values for the variables are at the optimal solution, and which constraints are binding and which ones are not. Okay? So this is something that we can easily get from the simplex method. Right? Then there's something called the sensitivity report. Now, if you look at it, it says final value, and it says reduced gradient. And similarly, for the constraint, it says final value, and it says Lagrange multiplier. So these things tell you what the sensitivity for various problem parameters are. How the solution changes with changing some of these parameters. Let me interpret the constraints for you. This just says that if I increase the right-hand side of the first constraint by a small amount, there is no change in the objective value. That's what the 0 there means. So in other words, if instead of this constraint, I make this, 6, 5 plus some small numbers, nothing changes, is what this tells me. If your increase is small enough, nothing changes.
That's not surprising, right? When this was 5, you already have a slack. So think of this as some kind of a resource, machine time. If I give you 5 units of machine time, you still end up using, 3, let's say. Suppose I offer to give you 6. Would you change things? The answer is no, because already you're using up less of this resource than what you have available. So offering you an additional unit of that resource is not going to give you any additional profit. Whereas for these two things, you may get a positive profit. And in fact, that's what those numbers say. That for every additional unit of the second resource, you can increase your profit by $1. Likewise for the third thing. Then there is something called a limits report. Actually, let me go back to this. Just want to show you one other thing. Under options, so when you assume a linear model and solve it, look at the sensitivity report, you see a slightly different looking report. And so this is particularly appropriate for a linear programming problem. And what it says is the following. So these are the final values. We will know what reduced cost is in a little bit. The objective coefficient is this. The allowable increase and the allowable decrease. So what do these two things mean? The objective coefficient is 2 if I increase the objective value, if I increase that coefficient by any amount that I like. What that tells me is that x1 will still be a basic variable. It will still be a part of the final basis. Similarly, I can decrease the coefficient of x1 in the objective function by up to 1. So if instead of 2x2, I make this 1.5x2, then x1 would still be a basic variable. If I decrease it further, if I make it 1, then you're at the borderline. x1 will still be basic, but if I decrease it any further, then x1 may become a non-basic variable. Okay. So it just gives you the range for which the current set of basic variables remains an optimal set of basic variables. Okay. Now observe that once I tell you what the basic variables are, that gives you a solution to the linear program, right? Because if I tell you what the basic variables are, then there is exactly one dictionary that you can construct, and that will give you, there's a solution associated with it, and that's an optimal solution, assuming I give you an optimal basis. So these two numbers just tell you the range of your variables, of the coefficients of the variables in the objective value for which the current basis remains optimal. Similarly, you look at each constraint and it gives you a range. Okay. So constraint 1, you can increase this by any amount you like. Okay, so that quantity 1 e plus 30 is just infinity. You can increase it by any amount you like, and this is the same basis will still remain optimal. You can decrease it by up to 20, and again nothing changes. Likewise for these. So constraint 3, for instance, you can make this up to 35 or down to 5, and in that entire range, no matter what this number is, the same basis remains optimal. It doesn't say the same solution remains optimal, it just says the same basis, which means you will still get an optimal solution by producing positive amount of x1 and x2 and setting the other variables, the non-basic variables to 0. So in this case, the non-basic variables are the slacks associated with these two constraints. They would still be 0, and therefore you can find the optimal values of x1 and x2 by just solving these two equations simultaneously. Okay? Any questions about any of this? Yes?
How do you differentiate between the basic and non-basic variables?
So how did it differentiate between basic and non-basic? Well, basic variables are those that have positive, non-basic variables are those, assuming that you don't have basic variables with 0 value. So, and that's something that we're going to get into in a moment. So in this particular example, for instance, x1, x2, and the slack associated with the first constraint, those three are positive variables. So all of those are basic. And x4 and x5, which are these two, those are non-basic. So what this says is, because constraint 2's allowable increase is 60, if I make this 55, so if I increase this by 20 units, then the same basis remains optimal. So that means x4 and x5 are still 0 in an optimal solution. And I can actually recover the optimal values for x1 and x2 by just solving these two equations simultaneously. Because if x4 is 0 and x5 is 0, these two inequalities have to be satisfied as equations. And so x1 will still be 20, x2 will be the difference of that quantity and 20 divided by 3. So when you solve a linear programming problem, not only do you get a solution to the particular data that you have, but you also get some additional information about the change in how the solution changes as you make small changes to the data. So you don't have to resolve another LP. You get some information from just looking at the solution itself, which is not such a huge advantage nowadays, where there's a lot of computing power. But still, even if you could solve another LP where these values change, you don't get qualitative insights about how the optimal value changes as a function of this parameter, let's say. Whereas this kind of analysis gives you that qualitative insight so that you know that this is the dependence that this parameter has on my objective value. Okay? Now, why is this useful? Well, often data for linear programming process, or for typically any model, are estimates. You make, you sort of measure things and make some calculations and arrive at what are best guesses of these coefficients and so on, which may not be exactly accurate. Right? They may not be the right numbers in reality, but they are reasonable approximations. So if you get a solution so you make estimates, you solve this linear program, you get a solution. If that solution is highly sensitive to the particular data that you have, then that's a little worrisome, right? Because maybe if I perturb the data a little bit, something completely different becomes an optimal solution. That says, maybe you should pay more attention to getting better estimates of your data. What's often the case is that the optimal solution, what you do, doesn't actually depend on the data in such a way. So often you observe solutions that are robust, that if you modify things, as long as the changes are minor, the same essential structure of the solution remains. So for instance here, if I make small changes to the data, the optimal values change, but they are still determined by the same set of equations. So this would be, this is machine capacity, inventory, and, worker capacity, let's say. This just, the optimal solution, one way to look at it is saying, produce 20 units of X1 and 5 units of X2. Another way to look at it is, okay, the machine capacity is not the key determinant. It's the inventory constraints and the worker capacity that actually determine what we can produce. So those are the two things that are important. So the second observation, while giving you the same solution for this particular data, is actually much more useful because it just says, what resources you should focus on. If you have the option of acquiring additional resources, then these are the ones that you want to increase, not that one. So there are many ways of reading an LP solution, and the actual numbers are perhaps the least important part of it in a real problem. Okay. Any questions? Okay, so
let me see how I can. Okay.
So that's going to do it. Yes.
Just about the thing that you said about if you decrease certain variable or the coefficient in the objective function by a certain number, it becomes a non-basic variable.
Mm-hmm.
What would be the consequence of one of only two variables becoming non-basic?
Oh, okay. So first of all of the sensitivity stuff that I told you about is changes to only one parameter, assuming everything else remains the same. So I didn't say that, but I should have said it. So when we talk about modifying the coefficient of this, it's assuming that this is fixed at 3, just looking at changes here. And that's orthogonal to the question that you asked, which is, what happens if you increase it or decrease it beyond the allowable range? So in that case, you know that the current solution is no longer optimal. Okay? And there are ways of getting to an optimal solution starting from the current solution. So you don't have to resolve your linear program from scratch, but you can start from your current solution and then do simplex iterations, for example. There are nice ways of doing re-optimization. And as you can imagine, re-optimization is an important issue in real life, where you have a huge LP, you solve it, and then you realize that maybe you should have changed something. Then you don't want to actually solve the whole thing, because you could imagine linear programs taking days to solve, and redoing the whole thing might be a waste of time. So there are very efficient ways of re-optimizing, and when we discuss sensitivity analysis, the theory, you will learn a little bit about it. There are also qualitative there's also qualitative understanding of how, what the change is like as you keep varying these numbers. Okay? So if this, as I keep increasing this, obviously my profit is going to increase because I get more money, but the increased profit, the amount of increase that I get for each unit would actually go down. There are things of the results of this form that we may or may not get to in this course, but they exist. So in general, all of these issues come under are studied under the name of what are called parametric linear programming problems, where you assume, you're given a linear program and there's a certain parameter. It could be a constraint coefficient, it could be the right-hand side, it could be an objective function coefficient, and you want to understand how Z star depends on that parameter. Okay? And there's a lot of work on those things. Any other questions? Okay. So if you still have trouble with Excel,
then you can come see me in my office later today. And I can help you with the homework problem. But it really is fairly straightforward. Okay, so if there are no other questions, then we'll move on to the pitfalls of the simplex method that we began to discuss last time. Okay. So what I want to do next is quickly go through some of the issues that we identified as being a problem. And they all have to do with the simplex method, at least the way we discussed it, and how you get it started and how it ends. Okay? So we already saw in class that that it's fairly easy to construct linear programs that are unbounded, whose optimal values go up, can be made to any number that we like. Let's actually construct such a linear programming problem. So, for instance, you want to maximize x1, x1 plus x2 is at least 6. Something like this. This obviously so this is an example of a linear program. It's a sort of a trivial example of a linear programming problem. So the objective value is unbounded. But you can set x1 to any value you like. Right? So how would you? So when we do the simplex method, we want to detect situations like this. How do we know that a given linear programming problem is unbounded? Is the question clear? I mean, so this is an obvious example, but maybe you're dealing with really huge linear programs, then how would you discover that there's a way to improve things all the way to infinity? So let me write that down as an issue, and I'm going to address it very shortly. So detecting the one is unboundedness. Infeasibility. There's actually one other issue that's important. Let me write down something like that. So let's actually look at the following dictionary. Let me first deal with the issue that we identified by doing before. So suppose you have such a dictionary, right? What happens? First of all, is this an optimal dictionary? No, because you have x1 with a positive coefficient or x3 with a positive coefficient. So you could make those basic and continuous. What happens here? Let's say you introduce x3 into the basis. So you can increase x3. So if you increase x3, x6 goes up, x5 goes up, x4 goes up. So how large can you make x3? You can set x3 to any number you like, and that's going to drive up your profit to infinity. So this is an example of unboundedness. And if you think about it, this is the only way in which you can get an unbounded cost. If the problem is unbounded, eventually, assuming the simplex method is right, eventually you will get to a point where you will detect that there's unboundedness. And this is the only step in the simplex method where you possibly create something infinity. If there is at least one negative coefficient, then you're going to be limited by that row. So that takes care of unboundedness. So whenever you write down the dictionary, you observe some variable in the last row with a positive coefficient, such that all of its coefficients in the other rows are positive, then you have an unbounded problem. Of course, you could have an unbounded linear program with a bounded objective value, meaning you could have a linear programming problem with an unbounded feasible region, but your objective value is finite. Now, how could that happen? So again, in terms of dictionary, I can easily cook up examples where something like that is true. Right? So z is minus 2x1 minus x2 plus 0x3. So if you look at this last row with these other rows, so is this an optimal dictionary? So forget about this row. This is your last row now. Is this an optimal dictionary? The answer is yes, because all the coefficients are they're non-positive. Okay? But of course, this has an unbounded feasible region because I could introduce x3 into the basis, and I can make x3 as large as I like. All of those points are feasible. It's just that they're all optimal as well. So I can go in the direction of infinity. So I have an unbounded feasible region, except that my profit does not go up. So there's no reason for me to. So the simplex method, at least the way we discussed it, would not do such a pivot. Right? It would stop the moment everything here becomes non-positive. But you could get other optimal solutions by doing this. Now, nobody questioned, so I wrote down a dictionary. Nobody questioned me as to whether this corresponds to a linear program in the first place, or what the linear program was. Yes?
What is the linear program?
What is the linear program? Well, this is the linear program, right? We said anything here, so let me write down a linear programming problem corresponding to this. So the linear program is maximize
minus 2x1 minus x2 plus 0x3, subject to x4 equals 1 plus 2x3, x5 equals 3, that's the linear program. So you should start, so in other words, the way to go from LPs to dictionaries and dictionaries to LPs, and you should always keep this in mind. So anything that any linear program that you can construct, I can associate with it something like this. So anything that I want to illustrate, I could do so in a dictionary, keeping in mind that this is the linear program that we talk about. We always omit the objective, which is always assumed to be maximization. We omit the non-negativity constraints, and we write everything as equations. Now, if you read your textbook, you would know that your textbook does not talk about dictionaries. It talks about what are called tableaus, which are exactly the same as dictionaries, except that the variables are all rearranged and they are sort of implicitly carried over. So how does that work? Well, I can move all the variables to one side, right? So instead of this system of equations, I could say x4 minus 2x3 equals 1, and so on. This is a conventional way of writing equations. You have variables on one side and constants on the other. Now, notice also that once you have all the variables on one side, once you know that there are, in this case, 6 variables, you can just save a lot of time and energy by not having to write them every time. So I could just say, this is my x1 column, this is my x2 column, x4, x5, x6, and this is my RHS, the right-hand side. I could say my first equation is just x4 minus 2x3 plus 0, 0, 0, 0 equals 1. So just as we encoded a linear program into Excel, there's a way of encoding such a linear program in this form. Similarly, the second equation just becomes x5 plus 2x1 minus 4x2 minus 6x3 equals 3. And so any operation that you can do with a dictionary, you can do with Tableau, right? You just work with numbers, keeping in mind that this is what we are studying. So as long as you make this correspondence mentally, learning in terms of these and learning in terms of these are the exact same thing. Is this clear to people? So let me actually just complete so it's minus 1 plus 3 plus 4. So this is a Tableau representation of the first 3 rows of that dictionary. And when you look at a Tableau, you can already see what the basic variables are. So you have those corresponding to the identity matrix in the Tableau. The others are the non-basic variables. You could also add another row which captures the objective function value, and so on. So your textbook only talks about Tableau representation, and you can do a simplex pivot just in terms of the Tableau, right? If you identify a particular, an entering variable and a leaving variable, then there's a certain cell that acts as the pivot cell. So the coefficient of
the entering variable in the equation corresponding to the leaving variable. You make that a 1, and then you do these raw operations, and you recover the next tableau. It's exactly the same as the operations that we did in going from one dictionary to the other. Now, what is good to use? Well, the answer is, since they are exactly the same, it's entirely up to you. So you could do everything the way we did in class. You could do everything the way we did, the way it's done in the textbook. And it's even better if you understand that they are the exact same thing. The reason I like this representation, even though it's more cumbersome, is because you never forget the problem. It's not that you're operating on numbers in a meaningless way. And so somehow that makes it nicer. But I know a lot of people don't agree with that approach, so feel free to use something that you're comfortable with. Okay, so unboundedness is clear. If I want to deal with infeasibility, I also want to deal with another problem that might occur in the simplex method. So first of all, how do you deal with infeasibility? Now notice that we don't just, not only do we have to find a feasible solution, we also have to find a feasible dictionary to start the simplex method. Okay? So suppose I give you a problem that looks like the following. So maximize x1 minus x2 plus x3, 2x1 minus x2 plus 2x3 is equals 4, 2x1 minus 3x2 plus x3 is equals negative 5, and so how do we get started if we are given a linear program that looks like this? What would we do as a first step? Well, as a first step, we would still convert it to standard form, just get all equations and all non-negative variables. So I would just say this is plus x4 equals 4 plus x5 equals negative 5 plus x6 equals negative 1. So, of course, you could use x4, x5, x6 as your set of basic variables for the initial dictionary, because they occur only in one equation with a coefficient of 1, and they don't occur anywhere else. And this is the trick that we use to get started in the example that we discussed in the previous lecture. Why does it not work here? Yes?
The negativity of the...
Because these numbers are negative, right? So if you write down the initial dictionary, the second row would have x5 equals minus 5 minus 2x1 plus 3x2 minus x3. In particular, x5 has to assume a negative value. That's not allowed. So you don't have a feasible dictionary. Of course, that's the same as saying that the origin, setting x1, x2, x3 to 0, is not feasible for the original problem. So that's why we are having this difficulty. So how do you get around this?
The times something to the right side, multiply by just one of the ones that have the negative.
Multiply by negative 1. This entire equation. Well, if you multiply by negative 1, you have a minus here.
What if you minus something?
What if I minus something? So when I do this, well, if I use a minus sign for x5, then x5 has to be non-positive as opposed to non-negative. So obviously we're not going to get around this problem by
some simple change of sign, something, right? I mean, this is, you know, the question really is, how do you know that this linear program is feasible? I mean, maybe these constraints are incompatible, right? If you somehow give me a feasible initial dictionary, then you're telling me that the problem is feasible because you found a feasible solution to the problem. Yes?
I have a question. Why we cannot make x5, x6 negative? I mean,
That's because all of these have to be non-negative, right?
well, I mean, all we should care is just x1, x2, x3 are not negative. I mean, if there is a solution, x1, x2, x3 are positive and the x5 and 6 are negative, that's still a feasible solution.
Well, so here's what I would do. If you accept that, I would set x1 to be 1,000,000, okay? And so remember that this constraint originally was 2x1 minus x2 plus 2x3 is at most 4. Okay? So I could set x1 to be 1,000,000 and x4 to be -1,000,000, and there's a problem, right?
Okay.
So to preserve the relationship between the original problem and the new problem, you preserve solutions if and only if these are all non-negative. Okay. So is the issue clear to people? So of course, if you're able to write down a valid dictionary, you're in effect saying that the problem is feasible. So if I give you a problem, you know, that's 100,000 variables and constraints, that's actually infeasible, then no matter what solution you have for addressing this difficulty, that solution procedure should come and tell you, look, this problem is infeasible, I don't even know how to get started. So somehow embedded into resolving this issue must be a test for feasibility of a linear program. Okay? Is that clear to people? Okay. So let me tell you what the solution is, and we'll continue on Tuesday. So, of course, we could do the following. Instead of x4, x5, x6 alone, I could say, I'm going to add new variable A, new variable B, and a new variable C to these equations. Okay? And I'm going to let A, B, C also be non-negative. Okay. And my first dictionary now is going to have A equals 4, and here I could do minus B and minus 2. So these are the variables that I'm going to add. Okay. And I'm going to let A, B, C be non-negative. And initially, I'm going to let A equals 4, B equals 5, C equals 1. So my initial dictionary is going to be A equals 4 minus 2x1. B equals 5 plus 2x1. 3, 6, 1. Okay? So I have a feasible dictionary. Yes?
There is no more for exciting.
There are x4, x5, x6. Thank you. So this should be minus x4, and this should be plus x5. Yes?
For this feasible thing, how would you convince people like you're gonna like preserve the original like?
Very good. So, of course, you know, I've added a new variable. This is also a gimmick, right? So we haven't done anything serious. We've just thrown in some new variables
so that we can get some positive quantities. But I want to guarantee that the solution to this system is also a solution to the other system. Right? Solution to this problem is a solution to the original problem. Of course, that is not true in all cases. So for instance, if I set A to be 4, B to be 5, and C to be 1, and everything else is 0, I satisfy this system, but all the x variables being 0 is infeasible for the original system. We already know that, right? However, what we could do is the following. I could find feasible values here, and I could try to minimize A plus B plus C. And let's actually understand what this means, and then we'll stop. If we try to minimize this quantity, okay? Now observe that A, B, C are all non-negative. Suppose this minimum turns out to be 0. If this minimum turns out to be 0, what must be true? A must be 0, B must be 0, and C must be 0. If A, B, C are all zeros, what must be true? Then you found a solution to this system. Okay? And therefore you found a feasible solution to the original problem. So if I can find a solution to this linear programming problem, where my objective is not the original objective, but it is to minimize this quantity, A plus B plus C, subject to these constraints and all variables being non-negative, if the objective value of that linear program turns out to be 0, then I have found a solution to the original problem. Now let's do the other way around. Suppose I solve this linear program, and my objective value turns out to be positive. What must be true? The original problem must be infeasible. Okay, why? Well, if the original problem were feasible, then I could use that feasible solution here and set A, B, C to 0, and I get a solution to this linear program with value 0. So what we've done is taken a linear programming problem for which we don't know whether there's a feasible solution or not. The problem of finding a feasible solution to the original linear programming problem can be cast as a problem of finding a solution to this new linear program with objective value 0. So this new linear program is a minimization problem. Okay? Now, of course, we can solve this linear program, right? Minimizing A plus B plus C is the same as maximizing the negative of that quantity. And we know how to solve that. So we would set up the simplex method to solve that linear program. If we find a solution with value 0, then we get a dictionary that's feasible for the original linear program that we started with. Then we continue. If at the end of this, we observe that the optimal value to this minimization problem is strictly positive, then we can conclude that the original problem was infeasible. So this problem is called the phase 1 problem, where you find an initial solution. What we did was the phase 2, which is you start with an initial feasible dictionary and continue. And the interesting thing is that to apply the simplex method to a linear program, you get started by applying a simplex method to another linear program. So this is like bootstrapping, as it's called. Okay? So it's a very clever solution to the difficulty that we observed, and we'll discuss this and other things in the next lecture. So just a reminder that there's a homework due tomorrow. I'm not going to be in tomorrow, so you can turn it in to the TA, or you can leave it in my mailbox in the lab. I'm going to assign a homework later today, and I'll send you an email once it's done. And your homework 1 is graded, and it's in my office, so if you want, you can come and pick it up. Okay.
A link we drop off tomorrow by noon.
By sending these well, I usually look at similar WordPress, like the 18, but